Hi, my name is Nicholas Kozenieski,
My name is Juan Perez.
My name is Ishan Patel.
and we're Team 1070 with Coach Youngmin Park. We chose problem C, standing against a mammoth, and today we'll explore a model and solution to this problem. So our motivation comes from hunters long ago, which had two options when killing mammoths. They either could throw the spear at it from afar, or brace it into the ground and let the mammoth come up close and run itself into the spear. In order to explore which option is better, we came up with a model using classical Newtonian mechanics. So our model starts by considering two forces on the spear, being just the quadratic drag and downwards gravity. And we use quadratic drag because using known numbers about the density and viscosity of air being 1.225 kilograms per meters cubed and 1.81 times 10 to the minus fifth Newton seconds per meter squared, we find a Reynolds number on the order of 10 to the 6, which is much greater than 1, indicating quadratic drag proportional to velocity squared. So setting up Newton's law and summing the net forces on the system, we include the drag force proportional to velocity squared and the force of gravity. So this gives us a coupled nonlinear system of ordinary differential equations. Unfortunately, because the system's nonlinear, this can't be solved analytically everywhere. However, a solution can be approximated around a neighborhood near the initial conditions using a Taylor expansion. So if the system were linear, then it could be written as follows, where the vector v dot is just some matrix times the vector v. Of course, this matrix A doesn't exist directly because of the nonlinearity, but we can expand the action of A on V up to first order using a Taylor series up to the order of the Jacobian. And using the definition of the Jacobian, we can calculate the partials with respect to Vx and Vy, and in our case, calculate the Jacobian as follows here. So subtracting, as shown on the previous slide, A of Vx naught y naught, we get that the perturbed system delta V dot is just proportional to the Jacobian at the initial conditions times delta V. And a system like this, just like in the single variable case, has a solution in the form of an exponential, except now in this case, we have a matrix exponential defined by the Taylor series. So if the Jacobian is diagonalizable, then we can write it as P inverse D, PD P inverse, where the matrix D is just a diagonal matrix of its eigenvalues, and therefore the e to the D would be e to each of those eigenvalues. And as we checked for our initial conditions, which we'll later elaborate on, the real part of all those eigenvalues is negative, which corresponds to the fact that in the neighborhood around Vx naught and Vy naught, the solution between that point and the point of interest does not diverge exponentially. So using the initial conditions of Vx naught, Vy naught, M, and CD, we can determine the Jacobian at the point of interest completely, and thereby solving the problem locally.
For the simulation, we begin by finding initial angles in which we can maximize the distance in which the Clovis spear point travels through the air medium. This gives us a rough estimate of what angle would allow us to obtain the largest final velocity as it reaches the mammoth. So our initial conditions was that the Paleo-American is approximately 5 foot 8 inches, which is just below 2 meters, and the Paleo-American throws it at a height of 2 meters above the ground, and we consider him to be at the x position of 0. Most spear throwers can reach a maximum velocity of approximately 15.58 meters per second, but in this case we'll assume that the Paleo-American is extremely strong and was able to throw it at a magnitude of 30 meters per second at an angle of 30 degrees. With this assumption, and the assumption that the drag coefficient of the spear through the air is approximately 0.15, which is the same drag coefficient of a javelin, as a javelin thrower throws it through air. So we calculate the drag coefficient using this graph we found on ResearchGate describing its relation to the Reynolds number. We calculated the Reynolds number for each of the media that the spear was traveling through, and we saw that it most closely resembled the ellipsoid geometry as it moves through air at standard temperature and pressure. So the formula for Reynolds number is shown on the right, rho being the mass density of the medium, v being the flow velocity, L being the characteristic linear dimension of the spear, which is approximately 2 inches, and mu being the dynamic viscosity of the fluid. So using this information, we were able to calculate it for these 5 primary layers, which we accounted for in our calculation: the hair, the skin, fat, and the muscle tissue within the mammoth. So we searched literature for an approximate value for each of these media by finding the mass density and all the other variables inside the Reynolds number. And we had to make a few approximations because some of these items have no measurements for them, which require experimental measurements in order to find. So one of the approximations we made for muscle tissue density of an elephant is that the muscle density of the elephant was approximately 1,060 kilograms per meter cubed, which is relatively close to that of the mammoth, we said. And we found that there wasn't that much information on these values. So we approximated it as a ballistic gel, which is used for projectile motion through muscle tissue. And we were able to get various variables through assumptions like these. Instead of treating each of the drag coefficients separately in our ODs and solving the OD 5 times, we instead took that homogeneous, an average of all the mediums that the spear was passing through, and we said that it was approximately 108.5. This simplified our calculations greatly. So our numerical solution we see here on the right, the top right, we see the value for Rx versus Ry as the Paleo-American throws a spear at the elephant and reaches a height of 3.6 meters, which is approximately the height of the mammoth itself, which is up to 3.7 meters. And it reaches at a velocity of approximately 17.1 meters per second. On the bottom right, we see the distance that the spear travels through the mammoth, which we consider to be homogeneous again. And we see that it only traveled 10 centimeters, which is inside of the fat layer of the mammoth itself. It never reaches the vital organs of the mammoth. And we see something similar for, not similar, but very different for streamlined drag coefficient, which travels much further. And we see that in the right graph that it travels completely through the mammoth, and its drag coefficient was approximately 0.04.
Now we want to consider the case where the spear was placed on the ground. Before solving, here are some basic assumptions. Firstly, the spear is very strong and will not break, and same thing for whatever contraption was used to keep the spear standing. The mammoth will run directly to the spear and hit it at the exact angle so that all the forces can be considered in one direction, essentially allowing us to reduce the problem to one dimension only. We assume that the mammoth is running at the spear at a velocity of 20 meters per second, which we found in literature to be about the top speed of mammoths. And that as soon as the mammoth touches the spear, it will begin to decelerate at a rate proportional to 1 over x squared. This leads us to consider that the mammoth will be imparting a decreasing force on the spear, but since the spear cannot move, then the spear will have essentially a driving force into the mammoth, supplied by the ground. Since the force decreases, with a decreasing speed, the driving acceleration plotted to the left would also decrease. Since the graph of 1 over x squared, however, does not get to 0, we approximated and truncated the simulation to 2 seconds, which would essentially correspond to the mammoth coming to a full stop in 2 seconds. Considering everything in the past slide, we can use the same ODE as the one for throwing the spear, except in one dimension. Here we can ignore gravity and use the same CDE as before, the drag coefficient, and we can get the 2 graphs to the left. Here the displacement is how deep into the tissue the spear was lodged. Note that the maximum depth in this case was about 43 centimeters, which is much higher than the previous method. The velocity calculation is a good check as well, as we can see that the trend is what we expect, a steep downwards trend. Comparing both methods, it appears that the bracing method is significantly more efficient as it achieves considerably more depth in the animal, probably even reaching organs and killing the animal. As we can see in this image, the following graphs show the same but for different initial speeds, which can essentially show that for about 7 meters per second, we reach a very similar point as throwing the spear. Thank you.